First of all, who am I? I am mostly a penetration tester, and my day job consists in reviewing code and try to find a way to breach into clients' code, also friends' code, to my own code, because when I code, I always try to code with a security-oriented mind. And lately, I noticed that one language is getting started in the programming scene, and it's pretty widespread. Google is sponsoring it, so yeah, it's widespread enough. It is a relatively young language because it's only 10 years old, and people are starting to use that mostly in security tools. Cloudflare is using a lot of Go, Google is using a lot of Go, and Docker, for example, is completely written in Go. So I started to think, what if I wanted to know how to look for vulnerabilities in some Go code? And I'm not talking about finding some O days in the runtime that I'm going to report and get patched the week after. Rolling new versions of Go is way too easy. If you find a vulnerability in the Go runtime, I'm pretty sure that it's going to be fixed incredibly fast. So I started to look into usual stuff. Memory safety, garbage collection. Those are pretty strong. I wasn't able to find any memory problem, not on a design level at least. And since the language is itself garbage collected, it is very unlikely to find some memory leak in some Go code. On the web server side, Go implements an HTTP server itself. So I went to look into it, and except for the complete lack of anti-csurf token, there is a pretty good anti-XSS filter. There is SQL prevention, so you're very unlikely to find those two. And lastly, it has built-in thread-safe constructs and data structures. So I didn't expect to find many race conditions either. So I started digging, because that's what I do as a job. New features usually bring coders to confusion. If you find a language that has new features, you should look into it. You should start to see if you can find anything wrong with those new features, not in the language itself, but on how do people expect them to behave. One of the main features that Go introduces are Go routines, which are basically threads, or at least they behave like threads. They are function calls preceded by the Go statement. So those are just functions run in a concurrent way, which means all the code that runs inside the function is concurrent with all the code around the Go statement. So the line before a Go statement is concurrent with the code called inside the Go statement. So I decided to give it a try. And I would ask you to look at this slide and try to think, what is the output of this code? It's just 5 lines of code, to which 2 lines are just parentheses. So from 0 to 9 included, on a new thread or on a new Go routine, print I, which should be easy to guess. And I expected it to be something like that. This is what I got, like 10 times 10. And since 10 is not even in the source code, the number 10 is not even in the source, I was like, well, I did not see that coming. And my reaction to this was, how would I expect it to print 10 times? The answer is in the fact that Go routines, in order to be very lightweight, had to give up something from traditional threads, they are multiplexed on them. If you spawn 1,000 Go routines on your server, you're not going to see 1,000 threads in your process. You're only going to see as many threads, as many operative system threads as your number of physical cores on your machine. The Go runtime is going to do the rest of the work for you. So it's going to schedule internally all the Go routines. The second problem in the code that you see before is that there was one free variable. The index of the for loop was a free variable, which means that it was captured, like in this example, inside a function that didn't declare or receive that as a parameter. In this example, I'm just declaring the hello string and I'm putting it inside a free var variable. And I'm using it from inside the code of another function that I declare in line. This is the way you create a lambda in Go. And if I call this function, which is called f, and I give it the argument closures, it prints hello closures because it kept the reference to that variable that will survive until the garbage collector notices that you're not using either that variable or the function itself anymore. So there is a dependency graph inside the garbage collector that keeps track of all the references to the variables, even if they are inside a lambda. Going back to these, we have a sort of mix of closures and Go routines, which is hell to debug. And not only because it is concurrent and parallel, but also because you have to keep in mind that I is only declared once in this code. So all the Go routines will have the same reference to the same piece of memory, which, once the cycle is concluded, will equal 10. So why do I always get 10 all the time? I run that code a million times. It always yielded 10 times 10, because the Go scheduler is not stupid. They try to optimize it as much as possible. So if the runtime sees that it can keep going and keep processing stuff, it will do that. Printing to standard output is a blocking operation. Creating a new thread is a blocking operation. It requires memory. So what it does, it tries to run as much as it can until it needs to perform some blocking operation. Unless you force it to yield, it will keep going. So this scheduling that I was dealing with was complex. It looked into my code. It knew what I was doing, what I was programming, and that caused the code to behave in a different way than I expected it to. This is the fix, which is even weirder than the problem. And this fix is not something that I made up because I would never, ever think of this solution. I took that from the official documentation. So this is something the Go developer and designers thought was a good idea, which is change the scope of the variable. If you redeclare I inside the loop, you're masking the original one, which is almost like giving that as a parameter to your Go routine, just in a closured way. And that below is taken from effective Go, which is a post on the official Go documentation. They redeclare a request inside the loop, just to avoid this problem. So, in order to understand what was going on, I needed to see something that they worked on to solve this problem in a better way than redeclaring variables inside your loops. So they provided the people with a sort of thread-safe data structure, which can be both buffered or unbuffered. Those are called channels. Channels are meant to solve most of these problems. Spoiler, they do not, but they're meant for that. You can either have a buffered one, which will mean that you have to read from a channel in order for the coroutine that is trying to write to it. In order for a coroutine to proceed, it needs the other coroutine to read from an unbuffered channel. If the channel is instead buffered, you can keep going and just write to the buffer and wait only when the buffer is full. So you can asynchronously fill a buffer and one other coroutine will pick it up. You can also close channels, which means that the other coroutines can keep reading from it until the buffer is empty, and they will then finish their loop. This is how you loop over a channel. You just use the channel as a collection, and when the channel is closed, somewhere in the code, the loop ends. So, one example. This is one very simple serve function that you could see in an HTTP server that just get a channel of HTTP requests and ranges over it in order to process them. But since you don't want your server to hang while processing an HTTP request because you want it to keep responding, this server was processing all the requests on a new Go routine, which is good, except it's not, because they were doing the exact same thing that I did in the first 10 line of code that you see. This is bad because they started giving the wrong responses to HTTP requests, because the last request was the one deciding who was going to respond to. So this is bad. If you're trying to look into Go code to try and find some race condition, Go statements inside any loop are a really nice spot to look into. I found some really nasty stuff, and they're almost not thinkable. And the only way to find those is not unit testing, because if you do unit testing, it's very unlikely to incur in a race condition, because you're testing what you expect to happen, not what you don't expect to happen. At this point, I said, okay, variable scoping is weird, but I can deal with it. I can find easy solutions to that. There is an aware scheduler that behaves nicely if you look at performances, less nicely if you look at the coder, the programmer, but who cares about them? So I wondered, how exactly aware is the scheduler? And I kept digging. A little bit of theory, sorry about that. On a machine, you have some operating system threads that are spawned in the exact same number as your cores on your server. Then you have some logical processors that are also in the same number as your cores that the Go runtime is going to spawn for you. Each logical processor has a queue of Go routines. And when a Go routine performs a yielding operation, like reading from a file, your logical processor is going to go to the next Go routine and execute that one instead. This task switch is almost unnoticeable. It is so fast that you can't possibly detect any thread switching cost in Go, because even if a garbage collection happens in this switch, which could happen, it is still going to take less than 2 milliseconds. Go runtime is incredibly fast in that, so you can save a lot of time in task switching, because task switching only happens when one processor is scheduled by the operative system instead of the other one, which shouldn't happen. So this is an example of how Go sees your code. There is a Go statement in your code which usually gets ignored when you spawn a Go routine that is very unlikely to get scheduled. Then there is some blocking operation, and in that case, the runtime is going to switch to the Go routine that you just spawned, because can't go on that one, so performs the whatever computation you have on the other one. If it encounters another blocking operation, like writing to a channel, which is a blocking operation, it switches back to the other coroutine, or at least it tries if data is ready. All those calls, and I mean every time your scheduler switches coroutine, it must be decided at compile time. Go runtime decides where a coroutine can switch its context during compilation. So there is no chance that a coroutine can get interrupted if the compiler didn't think that was a good idea. Which gets us to the second weird piece of code. Please try to guess if this line gets executed or not. Does this code print done or not? Anyone wants to try? Keep in mind that the first piece of code that I showed you was deterministic. It was 10 times 10 every time. So I didn't expect these to behave differently. It doesn't get printed, you say? Well, depends on the number of cores that you have on your computer. Which is even weirder, because when a coroutine is spawned, if you have another logical processor ready to get started and execute that, it's going to happen. So if you have two different processors, you get the runtime to execute both branches, which means when the sleep is encountered by the main coroutine, it will sleep. It will not find another coroutine to schedule, so it will keep waiting until it reaches the end of the program and exits. When at least one coroutine reaches end of the program ends. So also the endless loop will end. In the other case, if you're less lucky and you only have one core, the sleep will make the runtime schedule the other loop. And spoiler, this is not a yielding operation. Incrementing a variable is not something that yields control. It doesn't make sense because it is computational. There is no I/O. There is no blocking call here. So the runtime doesn't embed a scheduler call in this snippet of code, which means this coroutine will get executed and will never yield execution again. Coroutines have to yield this execution. And I discovered that because I was trying to deploy some code, some very simple piece of code which had an hard-coded main loop that only had to do some computation and a secondary coroutine that did some other job. I needed it to be fast and to do some computation. So it worked perfectly on my laptop, which is a quad-core, but on my Raspi Zero, it didn't run. Go is supposed to run on every architecture in the same way, which didn't happen for me. So if you want to try and see if the code you're inspecting or writing is vulnerable to this kind of thing, so to a coroutine taking control of your program, just set this variable to 1 at the start of your program. This will tell the runtime that you only have one core, and it will execute everything synchronously on one logical processor. Doesn't matter how many cores you have. And I have found some weird behaviors appearing only if you do that at the beginning of your tests. And this is where I found an actual production code containing this problem. This was taken from a parser, a JSON parser. They were analyzing UTF code points to parse the JSON. So they copy-pasted this very same snippet of code over and over in different places, which worked every time except one. As you can see here, they're ranging over a collection of which you don't see the type because Go has the column equal operator that allows you to say This variable is going to be of the type of the single element of this collection. So it allows you to write code faster, so without having to care about typing, which is terrible because once in all the code, they were passing a list of bytes to this Go routine. And if you have a list of bytes, this loop is never going to end because it overflows every time it reaches 255 and goes back to 0. So this is always true, and the code completely hanged. You wanted to ask something? OK. But there is something even worse. I was thinking, OK, if I can find a Go routine that doesn't yield execution, I can potentially block one core of the server. But that's still not enough. If you're trying to DDoS someone big and you block one core in production, yeah, that's somewhat of a damage, but that's not that much. You are very unlikely to find one blocking Go routine for every core of the server. So I needed something better, which is what I found, because garbage collection cannot possibly be executed asynchronously because it has to free memory. You cannot free or allocate memory asynchronously in a safe way if someone is concurrently trying to read or write that memory. For example, if you're trying to access an array and you try to append an element at the end, you need to be sure that you're not putting the element somewhere random, and you want to be sure that there is no way the programmer has to think about allocations. If you want to have a garbage collected memory safe language, the garbage collector has to be synchronous. Looking at the sources of the garbage collector, I found out that they called the main function that does that job stop the word. When a garbage collection is needed, the runtime stops everything and asks every Go routine to yield execution, which will happen at the next function call. So when the next function is going to be called by a Go routine, it will instead stop and wait for the garbage collector to start the word again. But it asks politely, which means that if you have a Go routine that doesn't want to give up context, the garbage collection will never happen. So if you can stop one Go routine in a non-yielding way, so you can find at least one Go routine in a server that does not yield execution, you get to stop the entire server. And you don't even need to have it run an infinite loop, as in the previous examples. It just have to be a very long computation, which the runtime doesn't want to interrupt. In that precise moment, nothing else can happen, because every Go routine is waiting for the garbage collector to restart the word, but the garbage collector is waiting for the blocking Go routine to yield execution, which will almost never happen. This is the very same example as before, but instead of a sleep, I'm just invoking the collector. You can put these in a Golang script and see that this never runs. Doesn't matter how many cores you have. You can have 128 cores. These will not yield execution. So this call to the garbage collector will not be ending. There are two solutions to this, and I saw both being used. One is always perform your computation in functions that you are sure the compiler will not compile in line, which is crazy. Don't do this. This is not the solution. This is just some weird guy on the internet telling me that I was wrong because he wanted to be right. Do not unroll your loop in a recursive way just to prove me wrong, please. That is just unreadable. The other solution is channels. And they perform pretty good. They're blocking, they yield execution, they allow you to pass data from one coroutine to another in a safe way. So they seemed to be a solution, at least for this problem. Spoiler, they're not. But I kept digging. So, coroutines have to yield execution. Scheduling must be taken into account. While you write your code, be sure to put some yielding call in your loops if you want them to be scheduled in a nice way. The scheduler is not preemptive. It cannot preempt a coroutine. It can only wait for it to yield execution. But then I wondered, coming from a context of web programming, I always used to see web servers kill processes when they took too long. If you're used to PHP, this is pretty standard. You can set a maximum execution time for your server, and when it sees that a process is taking too long to render a page, it just kills it. So I wondered, how do I kill a coroutine? You can't. Well, you can nuke the server farm, which is not a scalable solution. The routine can return, or the program has to end. There is no other way to stop a coroutine, because the go statement does not return anything. You cannot assign a variable when you invoke a go statement. The variable will not be compiled in any way, because go does not return a pointer to the thread or to the coroutine. They must be signaled and asked to end. So if you have some process in a server doing some computation, and the server needs to stop it, the only way is for the coroutine to be waiting for a signal, any signal. You can use a mutex, you can use a channel, you can use whatever you want, but the coroutine needs to see a signal in order to end, because coroutines are not garbage collected. If you lose the references to all the coroutines, and if you have no way to communicate with them, the garbage collector is not going to notice that. The coroutines will keep being in memory and will pile up. To solve this problem, the Go language provides a construct which looks like a nice solution, doesn't completely solve the problem, but tries to. Select allows you to read from multiple channels at the same time in a non-blocking manner. So if data is ready to be read, you can perform the computation you need. You can also read if the channel has been closed, because you can read two values from a channel. The first one will contain data, if there's any. The second one will contain false, if the channel has been closed. The default statement, if you put that in, the select will be non-blocking. If the default statement is not in the select block, the select will stop until one of the two channels here is ready. This is used to signal coroutines and send them information. If you want, for example, to close a coroutine, you just use a channel to tell it, hey, please stop, die horribly, some way, do something. So going back to PHP, which is pretty widespread, I still have to understand why. PHP allows you to set execution time for anything, and if that is exceeded, the runtime will kill it for you. And even if you don't set this variable, even if you don't call this function anywhere in your code, PHP is gonna set it to 30 seconds, which is a pain if you're trying to write something in WebSocket. But keep this in mind, PHP, like many other web-oriented languages, has a built-in system to prevent you from running a thread for too long. And so does Go. This is taken from the official documentation of the standard Go library. Timeout handler, I don't know if you can read it, but it says that it returns an handler that runs H, which is your handler, with a given time limit. So at first, I thought I did miss something in my analysis. I must have missed something because, as far as I understood, there is no way to do this. I was not surprised when I discovered that this is not magic, because the standard library is written in Go. So if the standard library can do something that Go can't do, you are missing something. This is a simple example. I just created the most simple HTTP handler that you can build because it only has the serve HTTP function. That function slept for 10 seconds and printed something to standard output. Then I run the web server with that handler with a 2-second maximum execution time limit. Turns out this gets printed every time because the standard library cannot kill your Go routine. No one can, unless you do unsafe stuff with the runtime, which requires you to use pointer arithmetics. But in that case, you're screwed anyway, so don't even bother. One nice thing about Go, which I suggest you to do if you're inspecting some code looking for vulnerabilities, is that it is very well documented, but it is documented only in one place, which is the standard documentation. And if you click on the name of a function in standard documentation, you are dropped to the source code of that function. Documentation tells you that it just runs for a given time, but it doesn't tell you how is that done. The source code does. So this is stripped from the original sources. It's just a piece of the original standard library. They are using a Go routine to serve your HTTP server, and they are setting up a timer to write into a channel after a certain amount of time has passed. Then they select in a blocking way from the two channels. If the Go routine ends first, it handles, if it means that it has handled the HTTP request. Everything has gone right, so all can proceed. If a timeout has occurred, the selector will proceed, but there was no code anywhere to tell my Go routine, please die. Because the interface for HTTP server does not give you a way to tell the server, please kill this Go routine if something is taking too long to end. You cannot possibly tell the runtime to kill your Go routine because you don't accept a channel. If you see my code, the serve HTTP gets a response writer and an HTTP request, which is not something that allows me to close my Go routine if it's taking too long. I cannot possibly write the code to understand that signal, so it keeps running. This is a nice piece of advice that I have learned by reading Go sources. If the standard library can't do something or can do something, so can you. The standard library is written in Go, pretty good one, pretty readable one, is very well documented and commented. If you have a doubt, if you think the documentation isn't enough, or the documentation doesn't give you what you want, click on the function, read the sources. I have found so many problems and so many missing things in the documentation that allowed me to find vulnerabilities in production code of some companies that were relying blindly on the docs. You should expect your code to behave as the sources tell, not just docs. There is another problem with the code that I showed you before. This is the solution they were implemented. They decided to use two channels, one to do some kind of job, and another one to end the processes in some way. On the main Go routine, they just sent some work to do. They started this Go routine, and when the Go routine needed to end, they wrote to a channel. Now try to find what's the problem with this code. Because there is a big one staring at us, which is what happens if you want to use more than one Go routine to do the job. It happens. You wrote code to run on one core, then you realize, hey, this fancy new server has two. Let's spawn two Go routines instead of one to do the job I need to be done. This doesn't scale. So the best solution that I saw, the most brilliant one, was that one. They spawned it 3 times, so they thought, well, we have 3 Go routines, let's tell them all to end. It works. It is a solution. Not a nice one, maybe. Doesn't scale well because you have to keep track of how many Go routines you have around, which the runtime should be doing, but it works. So if you want to have some unmaintainable code, that is the right solution for you. If you like to maintain the code sometimes in the future, you have to pick another solution, which is not the one on the right. This solution has a huge problem, but it is very well adopted, because if you look on Stack Overflow, how do I end a Go routine if I have many Go routines or questions like that? All the solutions contain something like this. I tried to correct the solution. I replied to the original thread, but my answer is not the most liked one. Doesn't look like they like it. In this case, they were spawning all the workers, and then they were writing to the done channel. In order to make it scale, they added some code in case of closure. They decided when someone signals this Go routine to close, propagate the signal over this channel and return, which kills the Go routine, which seemed like a proper solution. But what happens when the last Go routine tries to write to the channel? The main Go routine is not waiting for the last one to end. So you have a one Go routine, the last one of the chain, hanging. In this example, new channel created, Go routine, please die. It tries to write to the done, it reads to the, from the done channel, then it tries to write to it, but no one is listening, so it blocked. A Go routine is a very small thing. It requires only 16 bytes of memory, so it takes a long time before you realize what is eating up your memory. And if an attacker realizes that before you, that is going to end really bad, because you have no way to debug this, unless, of course, you are here. The right way to close Go routines is not this one either, because I saw that fix. So I write to the done channel, and then in order to allow the last Go routine to end, I just read from the sign channel. So I collect the signal at the end. Well, it doesn't work because, as I said before, you can't know how many Go routines are around. So in this case, what's the most likely thing to happen is that you have your main Go routine to write to the done channel, some Go routine writing back to it. And since the Go runtime is really aware of your code and where your code is in memory, it detects that the closest piece of code to the level 1 cache in your processor is the last that run, so it's faster to schedule that back again. So it will reschedule your main Go routine, which will read from the done channel, and all the other Go routines will not have the chance to read that signal, because the main Go routine took the signal from the channel, which is not there anymore. So they'll keep running which is even worse than the previous solution, which only leaked one. This other solution leaks all of them but one. This is the right solution. Just close the channel. When you close the channel, all the select statements that are trying to read from it will read from it a null value, but they will read from your channel, which means you can broadcast over a channel and have all the coroutines listening, ready to detect that your code is asking politely for your coroutines to end. And you can do that with the first loop that I show you, which is not very used, and I still have to understand why. Or you can also read from the channel the status of the channel, if it is closed. And if the status is not OK, just end your coroutine. The main takeaways from my journey into the Go runtime are: keep in mind race conditions. For loops only declare one variable. It's very tempting to spawn Go routines in loops. That is not a good idea, unless, of course, you mask your variables with variables that are called in the same way to prevent race conditions, which is unreadable. Always dive into sources. The standard library is written in Go, and most of that Go tries to keep these in mind. For example, you can interrupt an HTTP request by closing a channel, but that is not intuitive. You should always dive into what you're seeing that doesn't really adds up to what you expect it to be. Try to follow signals. When you see channels used in a way so that they're never closed, always try to see if there are Go routines expecting some values on them, because they will likely be leaked. And those bugs can go unnoticed for a long time, since Go routines are not that big. And last, check for yielding calls. Long pieces of code that do not return value or make blocking calls are atomic in Go. They cannot be interrupted, and no garbage collection can happen during those pieces of code. So always be sure to follow your code. If some attacker can find some piece of code in your Go library that allows them to call a function that takes 30 seconds to run, that is going to block all your server for 30 seconds. And that was it. Thank you. Do you have any questions about these? Yes. Oh, Cloudflare. Right, so the question is, does it still apply to Go 1.8? Yes, it does. And it will likely apply to all future 1. Star Go versions, because those are not ODays. Those are not vulnerabilities inside the runtime. Those are design flows. So they will stay there until we see Go 2.0, which will probably keep those, because those flaws allow the runtime to be efficient. Those are necessary evils to have an efficient Go runtime. There is no easy way to take that away. Like, for example, knowing when to schedule. That is important. Yeah. So you're saying so you're asking, okay, the proper way to yield is to use channels, but which one is more efficient, to use non-inline function or to use channels? Well, I didn't benchmark that. But one thing I'm pretty sure about is that it's pretty hard to foresee if the compiler is gonna compile your function inline or not. That is the only issue with that, because you could potentially have a non-inlined function that gets inline compiled in the next Go version, because that is not in the design document. They decided to keep that for them. They decide if in the next version they are not going to inline anything or to inline everything. So unless your function is deeply recursive, it's pretty hard to say if it's going to be inlined or not. Yes? What do you mean? If you want to give up context? So your question is, how can I yield execution? Yes. This call will tell the runtime to schedule another Go routine. This is a yield. I can't hear. So you're asking if these will still execute? Yes, if you have an infinite loop, it will keep running. No, there is no way from outside that Go routine to tell it to stop, unless it's listening for that call. Yeah, the Go language itself should be able to stop a Go routine, but it doesn't really do that. If you look into the sources, I don't know if you are a Go developer, but if you look into the sources, you see that the runtime doesn't really care about preemptive calls. So if you are asking, the runtime should be able to preemptively interrupt a Go routine, it could, but in this case, it does not. They didn't write it that way. They can't do that. So even if you use some weird reflection things, you still can't preemptively interrupt a Go routine. You can't tell the runtime to stop scheduling. Well, you can tell the runtime to stop scheduling a Go routine, but it means that with the reflection, you have to deep dive into the runtime, find a variable that is keeping track of that Go routine and raising that value with an unsafe pointer, which is not good in production. You could probably do that. I'm not sure. I haven't tried. But no, there is no simple way to preemptively stop a Go routine. Anyone else? Yeah. I did not contact them because they're aware of those stuff. I put together some piece of design documents from 2013 in which they were deliberately deciding to take this call. They decided that they were taking the risk of having some server somewhere paying the price for their choices instead of give up efficiency. They decided to do that. There is a document from 2013, and then there you can see it from comments inside the sources. If you read the sources, you see that who wrote the scheduler, which is only 4,000 lines long, not that big. You see that they are saying this will not allow us to know where this is going. Yeah, that was actually the purpose of this talk. But yeah, I was thinking about doing that after this, but these information are public. They're just not on the spotlight, under the spotlight. So yeah, if you think, yeah, you're right. There should be more awareness about these. I will contact the Go team about that. Thanks. Okay, so thank you for coming, and beware of Go routines.